probability, okay, so the sum of the probability must be 1, okay? So now I want to generate a sequence of x, okay? So this is the random number x, okay? In this domain A and B, okay? Yeah, very frequently A and B is from 0 to 1 or from -infinity plus infinity, okay? So it's depends on the nature of the distribution you want, okay? So now if I consider the integral, okay, fx, capital X, okay, capital Fx, okay. So this is the integration of the ft dt from A to X, okay. So this is the from A to B, okay, this entire domain, entire interval, okay, that's 1, okay. So fx, okay, for x, okay, less than b, okay, must be less than 1, okay. So the a, okay, from integral from 0 a to a, upper limit here, okay, yeah, is the b, okay. Then this by this normalization, okay, then we know that this is 1, okay. So fb is 1, okay. Now if I define a variable y, okay, equal to fx, okay. F is a function of x, y equal to fx, so y is also a function of x, okay. So now if I differentiate the y, okay, that means the differentiate of the fx, okay, yeah. So differentiate of this, okay, yeah, you give me the fx dx, okay, yeah. So this is all you learn in the calculus, okay. So when you differentiate this, okay, then you get the fx dx, okay. Yeah, it must be a function of x, okay, because anything else, okay, yeah, is a constant. Only anything depends on x, okay, is a variable, okay. So dy is equal to, because it's the function of x, okay. So the result must be a function of x, okay. So the differential, okay, yeah, is equal to this, and then the variable, okay, is x, okay. So it's fx dx. Yeah. So if I do the integration from 0 to 1 dy, so this is the, yeah, you see, yeah, a, okay, when y, you know, the y is the fx, okay, you know, so when x equal to a, okay, then fa is 0, okay, that means y is 0, okay. So when b, okay, then fb is 1, so y is 1, okay. So from integration from 0 to 1 dy is equal to this, okay. So you can see, okay, yeah, y is from 0 to 1, while x is from the domain, okay, is from A to B, okay. Now you see, this is the probability distribution of y is the constant in front of dy, okay, whatever the function here, okay. So it's 1, okay, right? 1 times dy equal to fx dx, okay. So fx dx, okay, is the probability distribution of the x, okay, and the y, okay, is 1, and that's the uniform distribution, okay, between 0 and 1, okay. So y has a uniform distribution in the interval 0 and 1. So now I can, this is the equation, y equal to fx, okay. So I can solve the x, okay, from y. If I know the y, then I can suppose I can solve x from this equation, provided this capital F okay, is some simple function. Okay, I can obtain the solution out of it. Okay, so that means if I can analytically solve this equation, solve this inverse equation. Okay, yeah, y is a function of x, and then you have to solve x in terms of y. Okay, so this x equal to the capital F inverse of y. Okay, yeah, this is suppose it's an algebraic equation, then this equation may not be too complicated. Okay, if it's x to the cube, okay, or x to the fourth, okay, some polynomial in up to the x to the fourth, then it's difficult to solve. Okay, yeah, but if it's an exponential function, then you know how to solve it. Okay, yeah. So anyway, this is the whether this can be solved analytically depends on what kind of function, capital F, you get here. Yeah. Yeah. So suppose, okay, you can solve this analytically, okay, then you get the x in terms of what, okay? Now, y is a uniform deviation, okay, from 0 to 1, okay, uniform distribution from 0 to 1. So y can be generated by the random number generator of uniform deviation in 0 and 1, okay? So once the y is given, okay, then I can compute the x, okay, by this, okay, by this solution here, okay? And then the x obtained, okay, will have the desired distribution fx. You see? So you use the uniform random number generator, generate this y variables, okay, random numbers, okay, and then plug into this equation here, okay, and then you obtain x. Okay? Yeah, since y is a uniform distribution, and then x is the fx distribution, so the x is the fx, okay, the x you get, okay, must obey this distribution fx. Okay, so is this clear? Any question on this? So this is rather straightforward, okay, uh, derivation, okay, and this usually called the heat bath method. Okay, yeah, the meaning, okay, you can, yeah, yeah. So this conventionally called the heat bath method, okay, yeah, or this called the importance sampling method, okay, yeah, yeah. Okay, let me go to an example. Okay, how can we use this heat bath method to generate the random number of any distribution I like? Okay, yeah. So for example, the random number generator with exponential distribution. Okay, so that means that fx, okay, is exponential minus x. Okay, so you can see the probability, okay, is the largest at x equals 0, and then the probability will be decayed, okay, as this exponential function. Okay, so I want to generate a random number x, okay, which distribute, okay, according to have this exponential distribution, okay. And the x, the domain x, okay, is from 0 to infinite. Okay, yeah. So now this can be integrated easily. Okay, yeah, integrate this. Okay, integrate this. Okay, from 0 to infinity. Okay, then you get 1 minus 1. Okay, yeah. So you see, you can hear. Okay, plug in e minus t dt. Okay, so you integrate this. Okay, then you get the, yeah, this is y. Okay, so you get the 1 minus e minus x. Okay, you see. So then I can solve this equation. Okay, so I can solve this. This is the y equal to fx. Okay, fx is this 1 minus e minus x. Okay, so e minus x equal to 1 minus y. Okay, and I can take the log. Okay, so I get this result. X equal to minus of the log 1 minus 1. Okay, so that's what I get. Okay, so for this exponential distribution, uh, I can apply this heat path method. Okay, and then as long as so this here I just generate a random number of uniform degree of y, then plug in this formula, then the x, okay, will obey the exponential distribution. Okay, so this is the simplest example. Okay, it works. Yeah, in general, the integral fx, okay, as well as inverse function cannot be done analytically. Okay, okay, so that means this integral here, suppose you can do it analytically, okay, yeah, but in some case, okay, if some distribution, okay, this integral you cannot done this analytically. Even though you can do this integral analytically, you may not be able to solve this inverse equation, solve this equation exactly, okay? Then you don't have an analytic solution between, or analytic relation between y and x, okay? Then this method, okay, yeah, cannot work in practice, okay, for such cases. Okay. Yeah. Of course, you can do the numerically, do the integration, and then numerically obtain this inverse equation, okay, numerical solution of this equation. But then this will be too time consuming, and then if you use this approach to get the random number, then this is the most tedious way of getting it, and it's not efficient because we need the random number, many random numbers. Okay, so it's impossible unless, okay, you can do this analytically, analytically, and also this you can solve this equation analytically. Okay, yeah. So numerical solution, okay, will render this method impractical. Okay. So that means that this step here has to be done analytically, and this can be done analytically. Okay, so at the end, okay, the relationship between y and x, okay, is a very simple analytic function. Okay. Yeah. So besides the exponential distribution, there's another example. Okay, this heat path method also works. Okay, there's the Gaussian distribution. Okay, so now I want to generate the random number x. Obey this distribution. Okay, so the mu, okay, is the center of the Gaussian. Okay, so that's the peak of the Gaussian distribution, and then sigma is the width. Okay, the half width. Okay, yeah, um, and this, okay, is often used in the Monte Carlo simulation. Okay. Yeah, for the Gaussian distribution random number generator. Okay. There's an algorithm is the best algorithm is called the box mirror algorithm. Yeah. The idea is very simple. Okay. Yeah, consider this point x1, x2 in the plane. Okay. Yeah, x1 and x2 both have a Gaussian distribution. Okay, so this is the x1. Yeah, have such a distribution, probability distribution. X2 also has the Gaussian distribution. Okay. And then with the center x1 as 0, okay, and then with the sigma equal to 1. Okay, so this is the simplest. Okay. Then the number of points in this area dx1 dx2 is proportional to this. Okay, so the probability of the distribution of the x1 times the p of x2. Okay, so this is two distribution product. Okay, so the product of these two give me this. Okay, Since this is on the plane, okay, then I can make a change of variable to the polar coordinate, okay. So x1 squared plus x2 squared equal to r squared, okay. And then the area dx1 dx2, okay, becomes the r d theta, okay. So this you all know, okay, in calculus or in physics, general physics, okay. Now, if I change the variable, okay, u equal to r squared over 2, okay, or r squared equal to 2u, okay, then I can write this as a e minus u, and then r dr is equal to du, okay, and then d theta is the same as the d theta, okay. So you can write this distribution, this Gaussian distribution, okay, in x direction, x1 direction, and also in x2 direction, okay, together, okay, and that in terms of the u, okay, u is an exponential distribution. The exponential distribution, okay, can be, as I already showed you, okay, it can be obtained analytically from a random number with a uniform distribution, okay? And the d theta is say from 0 to 2 pi, so it is also uniform. So I only need to rescale it, okay, 0 to 1, and then multiply the factor 2 pi. Then I get the theta is from 0 to 2 pi uniform distribution. Okay? So that means we have generated u, okay, with the exponential distribution, and u theta uniform between 0 and 2 pi. Okay? Then I get the x1, okay, because there's a transformation between u and theta, okay, or the r and theta. So this is the r, okay, r cosine theta, okay, and this is r sine theta. R is since r squared over 2 is equal to u, so that means r is the 2 square root of 2u, okay, so this is r, okay, so this is r, okay. So the x1, so once if I can obtain the u, okay, is exponential distribution. And then the theta is a uniform distribution between 0 and 2 pi. Then I use this formula to compute x1. The x1 will be the Gaussian distribution. Okay, yeah, obey this Gaussian distribution. Similarly for x2, yeah, is also I can use the sine theta. Okay, and then I get x2. So x2 is also obey the Gaussian distribution. That means I have two random numbers. Each of them obey the Gaussian distribution. Okay, you only need one random number with the Gaussian distribution. Then you just pick x1 or x2. Okay, will fulfill your purpose. Okay. So, any question about this method? Hmm?
Excuse me.
Yes.
I would like to ask, how do
Yeah.
we tell the distribution of u is in exponential distribution?
Oh, this is something I have to generate according to the previous. Uh, okay. So that means I have to generate another random number between 0 and 1. Then I get the x is the obey the exponential distribution. Okay. So this is the u. Okay. So you get the u. Okay. It's an exponential distribution. Okay. Right.
Right. Okay.
Yeah.
I was still thinking u is a substitution of r squared. So.
No. Yeah, u is since I know u, the distribution of u, okay, is e minus u, okay, du, okay. So that means u is obey the exponential distribution, okay, right? And
Yes.
then I can use this previous algorithm, okay, this one, okay, to generate the u, okay, u equal to minus log 1 minus y, and that means you generate a random number uniform random number, okay, and then use this formula and compute the U, okay, then you will get the U is exponential distributed, okay? Okay.
Okay, I see. So basically, I can treat the exponential to minus u as like a weight to the du, right?
Yeah, you can just use uniform random number generator to generate the U, which is exponentially distributed. Okay, once you use this formula. Okay.
Okay, thanks a lot.
Okay. Yeah. And then the theta is easy. Theta randomly distribute between 0 and 2 pi. Then you just generate another random number. Okay. Yeah, is between 0 and 1, and then multiply 2 pi. Then you get the data, okay, random variable between 0 and 2 pi. Okay. Once you get U and data, then you put in this formula, then you get the x1, either x1 or x2 will obey the Gaussian distribution. Okay. So all the x1, okay, will obey a Gaussian distribution, and all the x2 generated with this formula will obey Gaussian distribution. Okay. Yeah. Any other questions? Okay. Now let me show you the subroutine or the function. Or yeah. So this is the how we can generate the random number with the Gaussian distribution or this normal distribution. Okay. Yeah. So with Gaussian distribution with mu equal to 0 and sigma equal to 1. Okay. So this is the function you call. Okay. Yeah. A routine you call. Okay. And this is the n. Okay. Is the how many this random number you want? How many this Gaussian random number? Okay. You want. Okay. Random number of the Gaussian distribution you want. Okay. So first I have to have the numerical value of pi. Okay, pi is the arc cosine -1. So this is a pi. Okay. So this pi is actually up to the floating point precision. Okay, single precision. Okay, accuracy. Okay. And so I get the floating point number y, okay, between 0 and 1, okay, by calling this ran, okay, this is the, yeah, you can call any random number generator you like, okay, but this is, I just use the example using the ran d, okay, that is the intrinsic subroutine, okay, of the library, okay, the library, okay, yeah. So this is the integer, okay, and then divided by the 2 to the power 31 minus 1. Okay, then I convert it into a floating point number between 0 and 1. Okay, yeah. So I get the y, which is uniformly distributed between 0 and 1. Okay, and then with this y, I put in this formula, and then I get x. Okay, then this x. Okay, this is the actually this is the u. Okay, in the previous slide. Okay, and it obeys the exponential distribution, okay, e minus x distribution, okay. So so with this x is the exponential distributed, then I call another random number c, okay. So this random number is needed to generate the theta. Theta is a 2 pi times the c, okay. So this I get an angle theta, okay, is a uniform distribute between from 0 to 2 pi. Okay. So with the data and the u, okay, then I just use the formula square root of 2u times cosine data. Okay. And then, so this is the Gaussian uh, uh, distribution. Okay, random number generated with a Gaussian distribution. Okay. And then I cast it to the fold. Okay. Yeah. The reason I have to use double here because just try to make them, I mean, because in the algebra here, okay, the log and all this, okay, yeah, require higher precision in order to make it more accurate. Okay, so yeah, here I use the double. Okay, well, you can use all the double all the way. Okay, then this will be double. Okay, and then after you get the random number, double random number, you can cast it to the fold. Okay, so no problem with it. Okay, so but the operation here, the computation here, okay, is better done in the double precision. Okay, such that okay, yeah, the precision would be keep well. Okay, even after these operations. Okay, especially this x. Okay, yeah, just take the log here. Okay, so okay. Any question of this? Mhm. Yeah, here I only keep one set of the Gaussian distribution, Gaussian random number generator. Okay, uh, so only one set. Okay, the one with the cosine. Actually, the if I use another set of the, I have to keep another set. Okay, data one. Okay, or yeah, another array. Okay, then using the sign, okay, then another array will be also a Gaussian distribution. And these two distributions are independent Gaussian distributed random number random numbers, okay? Yeah. But usually we don't need two set of random number with the Gaussian distribution. We only need one set. So distribution, I only use this one of the formula, okay, just one of this formula to get one set of the Gaussian distributed random number, okay. You see, this is since you have the U and the data generated, so you get the x1 and x2, okay, and x1 itself, okay, all the x1 will obey the Gaussian distribution, and all the x2 will obey the Gaussian distribution, okay.
Excuse me, I have a
Yes.
question.
Yes.
Why is x1 and x2 independent? If we see the formula, x1 and x2 relate to each other by the cosine and sine. So if we have the same u and the same theta, then x1 square of square of x1 and square of x2, the add will sum up to 1, right?
Yes. Yes. Yeah.
Then why are they independent?
Well, yeah, if you look at it from this way, okay, they seems not they are related, okay, they are related, okay. But I'm saying that x2 itself, okay, and x1 itself, okay, is two sets of Gaussian random number with the Gaussian distribution, okay, yeah. So
yes, but
because yeah, you see, we are having two variables, okay, u and data, two random variables, okay. So for example, we have a two also can generate two random number, okay, two random number, okay. So you see this x1, x2, and then we convert it to the change of coordinate to u and data, okay. So now you have the U is a random and data is a random, okay? So in this way, okay, and I would think, okay, x1 and x2 are independent, okay, even though you think, okay, cosine data and sine data are related to each other, okay, you look at just one number, okay, they are related, okay, but if you look at the entire sequence, okay, then these two sequences, okay, presumably are random, okay. I mean the random means the sequence in x2, they are random in a sense, okay. Yeah, and the sequence in x1 is also random in itself, okay. So I'm not saying these two sequences, okay, have no correlation, okay. So the randomness, okay, is in the the sequence X2 itself, okay, and the randomness of this sequence is in this sequence itself, okay. But we are not saying so these are completely wrong, okay. You take X1 and X2 together in the same sequence, then there will be a mistake. You see, yeah, because in that case, then you have two numbers in your sequence. They are really correlated, okay, yeah. But if I separate these two sequences, okay, then these two sequences can be regarded as two different sequences of random number, okay, and then it can be applied to, yeah, for different used for different purpose, okay. Of course, you cannot mix X1 X2 together, and then these two X1 X2 together would not form a really random Gaussian distribution, okay, numbers, okay, yeah.
So do
Yeah,
you
that's
mean
what,
that if we
yeah,
want to get one sample of X1 and one sample of X2, we need to sample
yeah.
the theta twice?
No, I'm not saying that. You just sample theta once, okay, and also the U is only once, okay, yeah. But I'm saying X1, the sequence of all the X1, okay, will be one sequence of the random number with the Gaussian distribution, and all the X2, okay, generated, okay, since every time you generate the random U and theta, okay, so you get the random X1 and also the random X2, but you never mix X1 to X2, okay, yeah, that's the point, okay. So you get one sequence is entire composed of X1. Another sequence completely composed of X2. Okay, and these two sequence, these two set, okay, they have obey Gaussian distribution. Okay, and you can use it for different purpose. Okay, if you have a say a problem, okay, with two, you need a two set of Gaussian distribution. Okay, then you may do that. Okay, yeah. But you cannot use them together, okay, as a single sequence of the Gaussian distributed random number. Okay, because in that case, then the number are not completely random. Okay, because this you have two numbers, okay, in the sequence, okay, they are always in the cosine sine, okay, this relationship. So, okay, yeah. Yeah, I think of course it's better to only just use one sequence, okay? Never touch another sequence. Then this is maybe the best, okay? Yeah, yeah, okay. Yeah,
Okay, thank you.
yeah, okay. I'm just saying that okay, you have an option, okay, to use the X2 sequence or X1 sequence, okay, and also you can have use the X1 sequence for one problem and the X2 sequence for another problem. Okay, but you cannot mix these two sequences together. Okay, yeah. Okay. So you see the routine here. Okay, never have the cosine and sine. Okay, two sets to get together. Okay, yeah. Yeah. To solve most problem, you only need one sequence. Okay, you don't need two sequences of the Gaussian. Yeah, if you need two sequences of Gaussian, it must be in different contexts or different stage of your problem. Okay. Yeah. But anyway, this is not time consuming to generate this Gaussian sequence. So yeah, we never bother to use the another set of the Gaussian random number. Okay, either cosine or sine. Okay. Yeah. Okay. So I think this is the finish the lecture 7. Okay, which I did not have enough time to complete last time. Okay, let me. Is any question about the random number? Any other questions? Yeah. For today's or previous lectures. Yeah. There's something. Last lecture. Okay. There's it's quite going very fast. Okay. But the idea is that always to use this irreducible machinery twister, okay, or this machinery pan, okay, yeah. So machinery pan, this is the I think this is the most fundamental mathematics for the random number generator, yeah, because this is the rigorously mathematically proved, okay, yeah. Yes. So this is the primitive polynomial. Okay. Yeah. And mostly, okay, people only use this primitive trinomial. Okay. Yeah. And Fy is a 1 plus y to the power q, 1 plus y of p. Okay. And p and q, yeah, they are. This is the two, yeah, the p to the power p. Okay, yeah, is a minus 1. Okay, is a prime number. Okay, and this is the also irreducible. Okay, polynomial over the GF2. Okay, so then in that case, for the bit itself, okay, would have the maximum period. Okay, yeah, as I said here, yeah, both p and the 2p minus 1 are prime numbers. Okay, yeah, this is the for the bit. Okay, that is the maximum period. But if y, okay, is not the bit, okay, it's a number, then it's not guaranteed. Okay, yeah, but provided, okay, all the bits, okay, in the integer, okay, they are linearly independent, then the maximum period can be guaranteed. Yeah. So to attain that, okay, would not be easy because it involves R by P matrix of elements of bits. Okay. Yeah. To generate the random bit, okay, is mathematically rigorous. Okay. But to generate the random number, okay, using the this machine pan, okay, and also using this this irreducible polynomial, okay, then this some tricks, okay, and especially for the initial seed. Yeah. And the most advanced algorithm in this approach is this machine pan, okay, because it's this is the machine twister, okay, yeah, because it is kind of mixing many different sequence of the shift register algorithm, random numbers, okay, together, and then can get the good randomness as well as the a very long period. Okay. So this is the 19937 is a prime number. And then 2 to the power 19937 minus 1 is also a prime number. Okay. And then this machine-leadership presumably can the period, okay, is as long as this. Okay. So yeah, so it's quite contribute, okay, to attend that. Okay. Okay, now let me move on to the next topic. Okay. So so I will talk about the Monte-Carlo simulation, the importance sampling, and the Metropolis algorithm, and then the Ising model, and also the Monte-Carlo simulation, two-dimensional Ising model. Okay. The reason I talk about the random number because the Monte-Carlo simulation or any this simulation, okay, requires the random numbers. Okay. Yeah, as you know, the computer simulation has become the integral part of the basic and applied sciences. Okay. And it's actually serving a bridge between the experimental and theoretical approaches. Okay. Yeah, in science, we can do experiment and also you can do the theoretical study. But eventually you have to match. Okay. Yeah, theoretically you can do prediction. Okay. Modeling. Okay. But then the theoretical prediction, okay, has to be in agreement with the experimental result. Otherwise, the theory is wrong. Okay. Yeah. In science, okay. Yeah, the discovery must be come from the experiment. Okay. Yeah, you have to do the new experiment. Okay, to get the new result, and that new result has never been predicted by the theory. Okay, then this is a big fool. Okay. So experimental approach and the theoretical approach, yeah, cannot be quite independent. Okay, we need to go together in order to make the advancement. But sometimes the experiment is too difficult to do. Okay, yeah, so it is required to do some simulation. Okay, before we can build the apparatus, and yeah, because when you have to, it's very expensive to build the apparatus which can do whatever we want to have in mind. Okay, to discover. Okay, yeah. On the other hand, for the theory, okay, it's often difficult to obtain the analytic solution. But we need some idea, okay, what's going on, and then understanding what's the physics, okay. So even without analytical solution, then we may try to get some numerical solution to get the insight to the problem. Okay. Yeah. Yeah. Sometimes you can do a modeling, but modeling often is oversimplified and yeah, missing some important ingredients. Okay. Yeah. So yeah. So as I said, okay, for the theories, okay, often difficult to obtain exact analytic results or exact solutions. Yeah, or even numerical solution by direct method. Okay, you want to solve some problem, solve an integration. Okay, just by the brute force, and it will be quite difficult because the integral may be very high dimension. Okay, yeah, it's almost impossible to do a numerical integration. reliably. Okay. Turns out the method, Monte Carlo simulations with important sampling, okay, is the only viable way to obtain the numerical solutions, especially in the case of you have to do the integration, then the Monte Carlo simulation, with the important sampling, okay, is the only viable way, okay, with the computing resources you have, okay, limited computing resources, okay. For experimentalists, okay, it's necessary to simulate the physical parameters of the detectors before they are built. Okay? Also, some experiments are too expensive or difficult to perform in practice. Okay, so we have to rely on the numerical simulation to provide the answer. Okay, in physics, we often have to deal with a large number of degree of freedom. Okay? For example, in the field theory, okay, in the electromagnetic field theory or any other field theory, okay, the field variable is in the at any point of the space-time, so you have an infinite number of the field variables. Okay, and also if you consider electrons in the atom, then for some atoms that the electrons very large, okay, 100 even, okay, more than 100, okay, so 200, okay, so not to mention the number of atoms in a rock. Okay. So you want to understand these systems, okay, then you have to very often you have to do the integration of very high dimensions, because each degree of freedom, okay, will require one dimension of the integration. Okay. So you have to do the integral of very high dimension. And exact solution of this integral have not been known except for a few simple models. Okay, so you see, such a high dimension integral usually is difficult to get the exact solution. Okay. Even you want the numerical answer, okay, but you just do it straightforwardly, okay, using the trapezoidal rule or Simpson's rule, and also often our question, okay. Because the dimension, okay, is too high, okay. When you do the digitization, okay, the number of points, okay, is our question, okay. So for example, I want to get the classical partition function of a gas of n atoms at the temperature T, okay, and this n atoms of gas, okay, they are interacting by this pairwise potential, okay. So only two of them have interaction. Any two of them have an interaction, okay. So only two particle interaction, okay. But so I have to sum over the potential between all pairs, okay. So this is a simple model, okay. And this is the total energy, okay. Total potential energy of the system, and this is the divided by 1 over kT. K is the Boltzmann constant, okay? And T is the temperature. So this is the energy over the kT. Okay, so this is the Boltzmann distribution. Okay, so this is the classical probability. Okay, for this gas of the n atoms at the temperature T. Okay, but since each atom, okay, has can be at any positions, okay. So I have do partition function sum over all the probability of such a or sum over all possibility of such a such a probability. Each configuration, okay, has a probability proportional to this Boltzmann factor. So partition function is sum over all the probability. That means to sum over all possible configurations, and each atom has these three coordinates. So I have the three-dimensional integral, and this R suppose from -infinity to +infinity. Okay. So this integral has a dimension is 3n. Okay. Yeah, because each atom has three-dimensional integral. So altogether has 3n. Okay. Now suppose each coordinate takes 10 different values. Okay. So x direction only 10 points. Okay. Then the integral must be varied at 10 to the power 3n points. Okay, because each coordinate has the 10 point. So and each atom has a 10 to the 3 points, and then there are n atoms, so to the power n, so 10 to the power 3n points. So even 10 points in each direction. Okay, yeah. If n okay small, okay, n is 2. Okay, is the 10 to the 6. Okay, yeah. It's not 10 to the 6. Actually, is not the small number. Okay, you have to evaluate this probability. Okay, at 1 million points. Okay, yeah. So it's still manageable. Okay, but if you have n is 10. Okay, so 10 to the 30, then these are all questions. It's impossible to do it. It takes too long. Okay, impossible. No matter what kind of supercomputer you have. Okay, yeah, it cannot be done. Okay, so this direct method, okay, or direct integration, okay, yeah, easily meet the limit. Okay, yeah, so you cannot just do it in this way. Okay, even if you want a numerical solution, okay, you cannot do it directly. Okay, so with the limited computing resources, okay, the only way you can do it is by the Monte Carlo simulation. Okay, yeah, so Monte Carlo simulation. So the idea of Monte Carlo integration is not to evaluate the integrand at each point. Okay, yeah, because those points too many, 10 to the power 3n points is too many. Okay, yeah, yeah. So if I can just sample a point with a probability proportional Boltzmann distribution in the integrand, okay, that means the higher probability of that point, that configuration, okay, that point, okay, that point in the configuration space, okay, then the probability of getting this point will be higher. Okay, the sampling probability will be higher. Okay, so that means I have to go over all the points. I just have to go over the points, okay, which have a higher probability. But I do not do it deterministically. Okay, I do it stochastically. Okay, that means I always maintain the say this is the probability. Just getting this point, okay, is according to the some algorithm, okay, and that getting this point, the probability, getting this point probability is proportional to the Boltzmann distribution. Okay, then in this case, then I don't have to vary. Okay, this Boltzmann probability explicitly. Okay, so I sample the configurations, sample the positions, okay, of these coordinates, okay, and according to this probability distribution, okay, then this probability distribution already been embedded in the sampling, okay. So after I get this configurations, okay, say this R1 to Rn, okay, K is M configurations, okay. And then each configuration, I just use this configuration to evaluate this observable, okay. And then sum over okay, and then take the average, okay. Then I get the expectation value of this observable. Okay, you see? So the more sampling you use, the more accurate the answer you get. And the error is of order 1 over square m. M is the number of sampling you have. So if you can afford to do more sampling, then you get a more accurate answer with a smaller error. Okay, but with your limited computing resources, okay, then you can just do whatever the largest sampling you get, and then you still get the error. Okay, you know what's the error of your answer. Okay, so this is the feasible way. Okay, viable way. Okay, you can get a good estimate of the integral. Okay, with the limited computing resources. Okay? Yeah. So such a estimate, such a Monte Carlo integral, okay, integrate answer, okay, by the Monte Carlo simulation, okay. Yeah, this must be better than the one which is by the direct evaluation, okay. So by the direct evaluation, okay, if you go through all the points, okay, there must be some points, okay, the contribution to the integral is small. That means that is the less important point, okay, not so important, okay. But you still have to use the same computing resources to evaluate that point, okay. So with the fixed amount of computing resources, Monte Carlo simulation, okay, always turns out to get a better answer, a more reliable answer, okay, yeah, than the direct method. Okay. So this is the merit of the Monte Carlo simulation. Okay. Yeah, even with the limited computing resources, I can still obtain the estimate of the answer, okay, which is almost impossible for the direct evaluation. Okay. Yeah, any question up to this point? Now, the crucial point is how do we sample these configurations? Okay, yeah, satisfy. You have to sample a configuration with a probability obey the probability distribution of your problem. Okay, and this probability distribution depends on what kind of problem you have. Okay, different problem have different kind of this probability distribution. Okay, yeah. Yeah, most commonly is this Boltzmann distribution, okay, which happens in the statistical mechanics and also in quantum field theory. And in that case, okay, the Monte Carlo simulation will work. Okay, there are some problems. Okay, Monte Carlo simulation may not work. Okay, so far still a big challenge is if you have a integrand. Okay, have a changing sign. Okay, that means the probability of the probability here distribution. Okay, is not positive definite. Okay, it could be positive, negative. Then you cannot use that as cannot interpret it as the probability distribution. Okay, then in that case we do not know how to do a simulation, because all the Monte Carlo simulation relies on the concept of the probability. Okay, stochastically. Okay, doing the simulation. But if the probability here, okay, this distribution is not the positive definite, then you cannot interpret it as a probability. And then we don't know how to do the simulation reliably. Okay, so this is one of the big challenge, okay, in the Monte Carlo simulation, and this is called the psi problem. Okay, yeah, this turns out in physics there are many problems, many physical problems, yeah, have this psi problems. Okay, so so we still do not have a good solution to them yet. Okay. Yeah. Okay. Anyway, before we tackle the psi problem, at least we should first do how can we do the Monte Carlo simulation without the psi problem first. Okay. Yeah. Okay. Let me begin with this one-dimensional Monte Carlo integration. Okay. Yeah, one-dimensional. Yeah, usually the one-dimensional integral, okay, does not require Monte Carlo integration because you can do it, yeah, by numerical integration. Okay, there are many methods doing numerical integration, very fast and reliable. Okay, and you all can get a good answer. Okay, here I just yeah, in order to talk about this Monte Carlo integration, then to discuss the basic ideas. Okay, I use this simple example. Okay, yeah. So suppose I have the integral, okay, from 0 to 1 fx dx. Okay, fx is any function. Okay, yeah. So for the Monte Carlo integration, okay, if I have endpoints, okay, yeah. So this endpoint, yeah, I have to sample endpoints randomly between 0 and 1. Okay, so I just get this endpoint with a uniform distribution. Okay, with a uniform deviation. Okay. And so each point have an equal probability being selected. And then in that, then I do evaluate the f at this point, fxi, and then sum over it, and then divide by n. Okay, then it's an answer. Okay, so these points are sampled without any I mean the uniform. Okay, yeah, equal probability. Okay, each point has an equal probability. Okay. So this can called simple sampling. Okay, yeah. So this is not the important sampling. This is because I do not sample a point according to some probability distribution. Okay, yeah. So this is called simple sampling. Okay, and the uncertainty of this evaluation, okay, can be estimated by the central limit theorem. Okay. So in the limit n go to infinite, okay. So now I have used endpoints, but now if the n go to infinite, okay, then the distribution of I is a Gaussian distribution, okay, with the variance sigma I square equal to sigma f square over n, okay. So that means yeah, if I take n very large, then if you do then each time you use the n, and then you get an I, okay, and then you use another n, then you get another I, okay, okay. Then this distribution of I is a Gaussian distribution, okay, yeah, and with the variance sigma I square, okay, equal to sigma f square. Sigma f is the variance of the f, okay, function, okay, yeah. So that means you can see here, and then sigma I square is the integral, the variance of the integral, okay, and then sigma f is the variance of the function fx, okay, and the relations is about 1 over n. N is the number of points, okay, you sample them, Okay, so the sigma f, okay, is this. This is standard way of computing the variance. Okay, you have endpoints, and then you evaluate the f at each point, and then square it, and then the average. Okay, minus the average square. Okay, so that is the that means the f square expectation value minus f expectation value square. Okay, so this variance. Okay. And the variance of the integral will be the variance of the function divided by n. Okay. So this is the central limit theorem. Okay. Yeah. So if n goes to infinite, then the distribution of I is a Gaussian distribution with the variance sigma I squared equal to this. Yeah. Yeah, you can numerically verify the central limit theorem. Okay. Yeah. By changing the n and then see how the distribution of the I is. Okay. And then you will see as n getting larger and larger, the distribution of I will go to Gaussian distribution, and then with the variance sigma I squared, okay, is equal to the variance of the sigma f squared for n. Okay, that can be verified numerically. Okay, yeah. Anyway, from this expression, or you can go to the mathematical textbook, okay, and get a proof, or you can just use the Wikipedia, okay, look up Wikipedia, and then you give you a proof. Okay, so yeah, from this expression, you can observe two important things. Okay, one thing is the sigma I, the variance of the integral, would decrease of 1 over square n. Okay, so that means you have a number of measurement. Okay, number of sampling. Okay, you get, okay, say if you increase 4 times of the sampling. Okay, then your error of the sigma I, okay, the error. Okay, sigma I is square root of the sigma I squared is the variance. Okay, sigma I, okay, usually it's called the error. Okay, of the mean or error of this integral. Okay, would decrease as a factor 1/2. Okay, 4 if n is 4 times. Okay, then the error will be reduced by factor 2. Okay, if you increase the measurement by 100, then the error will be reduced by what 0.1. Okay, yeah, 0.1 of the error. Okay, yeah, factor 0.1. Okay, so so this reason why I said, okay, in the beginning here, okay, the error here is proportional to 1 over square m. M is the number of the points, number of measurements, number of sampling. Okay, you perform in the simulation. Okay. Another important fact is the variance of the sigma I of the variance sigma I square. Okay, or the error of this sigma I is proportional to the sigma f. Okay. So sigma f, okay, is the measure. Okay, how smooth. Okay, how does the function f where changes. Okay, so if the sigma f is a constant, then this is the 0. Okay, so you can determine the integral by just one sampling. Okay, 1 point. But sigma f is small. If f is smooth, okay, then sigma f will be small. Okay, yeah. So so these two observations, okay, give us the idea, okay, how to proceed to the simple sampling to the important sampling. So in the limit, as I said, in the limit, if f is constant, then the sigma f is 0. Okay. Yeah. So then the integral can be usually exactly by only one point. Okay. You don't have to sample any x, okay, just sample one point x, okay, and then you get an exact answer. Okay. So so this is the how we can make the Monte Carlo simulation more accurate. Okay. So now you can introduce a wave function, okay, Wx, satisfy this condition, okay. So integral dx Wx equal to 1. So this wave function is more or less like the probability function, okay. Yeah. And we choose a W such that it behaves approximately as f, okay. It cannot be exactly the same as f, okay. If that is the case, then you are doing the same integral, okay. So just choose the Wx, a simple function, but it captures the main behavior of the f. Okay. So then in this case, then the fx over Wx will not be changing too much in this interval. Okay. So that means I have to fx divided by the Wx, the wave function, and then of course I have to times the Wx again. Okay. Now I change the variable here, dx Wx to be dy. Okay. So then I can do the integral here. Okay. Y of x. Okay. Because dy is equal to dx Wx. Okay. Then I can define this yx. Okay. As the integral of the Wt dt from 0 to x. Okay. So in this way, okay, the value of y is also changing between 0 and 1. Okay. So when x equals 0, okay, y 0, then it's 0. Okay. When x equal to 1, y 1. Okay. So this is upper limit. Okay. So since this is 1, from 0 to 1 is 1. So at x equal to 1, then y is also equal to 1. Okay. So the limit, okay, the limit of x, upper limit and lower limit the same. Okay. Both are from 0 to 1. Okay. Okay. And then this ratio, okay, you see the Wx dx, okay, merged together to the dy. Okay. Yeah. And the ratio, okay, is because x, okay, now I will change the variable to y, so I have to express x in terms of y, and here Wx also, x also as a function of y. So then everything is in terms of y. So this is the capital F of y. Okay. And then it becomes an integral, okay, y as a function of the variables y and then fy. So we are doing the integral, okay, in terms of y rather than the x. Okay. Now, yeah, then the uncertainty of sigma I can be minimized because the transformer function is very smooth over the entire interval. Okay. Yeah. So sampling the y from 0 to 1 uniformly. Okay. Amongst to sample x between 0 and 1 with the probability distribution Wx. Okay. You look at this. Okay. Because dy is equal to dx Wx. Okay. So y has a probability distribution probability distribution function 1, and the x has the probability distribution Wx. Okay. So yeah. So that means y is a uniform distributed from 0 to 1. But yeah, with this expression, okay, if you can solve, okay, x in terms of y, okay, then the x, okay, will distribute according to the distribution Wx. Okay. Now, since Wx has to behave very close, okay, to the f, okay, that means have more points assembled at those points where f is large. Okay. So Wx will be when Wx is large, then f is also large. That means I will sample the more points where f is larger. So that's more important contribution. Even because at those points when f is large, then the contribution to the integral will be larger. Okay, will be more important. Okay, so that's called important sampling. Okay. So that's the important sampling, and that's the essential idea of the Monte Carlo simulation. So in Monte Carlo simulation is the simulate the such that, okay, I sample this points, okay, sample the configuration, okay. The probability of sampling this, getting this configuration, is proportional to the probability of this distribution. Okay, yeah. So when the probability is high, then the probability of sampling this configuration will be also high. Okay, here I sample the x according to distribution Wx. Since Wx and f behave more or less than something the same, okay. So the higher W will be that the point f is larger. Okay, so that means the Wx is the probability distribution. That means that at such points it has a higher probability being sampled. Okay. So the whole thing, okay, summarized here. So I have the integral is from 0 dx fx, okay. But then I find a wave function. This Wx behave closely to the fx, but of course not exactly the same, okay. And the Wx presumably must be a simple function, okay, simple function, okay. Yeah, and then dy is dx Wx, and then yx, okay, is this integral here, okay, presumably after you integrate this, you can obtain the x in terms of y. Okay, so this can be, that means this integral can be done analytically, and also the inverse can be done analytically. Okay. Yeah, if all this can be worked out, can be done, then you can use this method, okay, to get the important sampling. Okay, so you can use the y with the uniform distribution, and then obtain the x, and then substitute to this expression here, the small f over w, and then sum over your sampling point, okay, and then you get the answer. Okay. So if you do the simulation in this way, rather than getting these endpoints randomly, uniformly, okay, then this is called important sampling. Okay. Yeah, because I sample the points according to the distribution Wx, and Wx, okay, is chosen such that fx Wx is the more or less is capture the behavior, okay, of the fx, okay. Even though this is a simple function, fx may be a more complicated function, but it captured the essential features of the function fx. Okay. So yeah, if all this can be done analytically, okay, that means this integral can be done, and the inverse, you can find the y x in terms of y. Okay, x a function, x as a function, yeah, how as y. Okay, then this important sampling can be done easily. Okay. Yeah. And let me give you an example, okay? Yeah, suppose fx is this, 1/1 plus x squared, and the integral is from 0 to 1. And this integral is can have exact solutions, power of 4. Okay. Now you can see, okay, this function is decreasing, okay. Yeah, it's something like that, okay. At x equals 0, there's 1. At x equal to 1, there's 1/2, okay, so it's decreasing, okay. So I choose this, okay. I choose this wx, okay. Yeah. I know this is this is a linear function, okay. It's linear decreasing, okay. All these coefficients here are fixed such that, okay, such that it satisfy this constraint, okay. So this is such that wx, okay, can be regarded as a probability distribution, okay. Yeah. So you can see that, okay, when I do the integral of wx dx, okay, that's equal to 1, okay. Yeah. Okay. Yeah. Now, choosing this wx, okay, as a linear function is good because I can do this integral, okay, easily, okay, because it's a linear function. So the integral here, after integration, I get a quadratic function, okay, and I know how to solve the quadratic equation, okay, so I can solve x in terms of y. So once I get once I use the random y from between 0 and 1, then I get x, and x will be have this distribution wx distributed as this wx, and this wx distribution will capture the features of this integral of decaying, okay, or of decreasing, okay, feature, okay, yeah. So if you implement the this importance sampling, okay, then you will see the importance sampling, okay, will give you much more error than the simple sampling, okay. Now, okay, so this is the actual simulation result, okay. So if I only use the 10,000 points, okay, to do this, to do this one-dimensional Monte Carlo integration, okay, or this integral, you only use the simple sampling. I get this, and then this is the error, okay. Similarly, if I use the 10,000 points to do the importance sampling with this wx, okay, then I get the answer this, and then the error. You can see the error is smaller, okay, yeah, much smaller than this one by an order, okay, by an order. And the exact solution is this, okay. So you can see, okay, no matter the mean value, okay, for the importance sampling is closer to the exact solution, and also the error, okay, is a smaller, okay, yeah, okay, yeah, yeah. Let me go to the. I have a sample code, okay, so let me go to a sample code and then show you, okay, how actually, okay, yeah. I hope this is still connected, okay. Let me see. Oh, yeah. Okay, good. Now let me switch the screen. Okay. Let me go to the. Let me first stop this screen and then use another screen. Yeah. Okay, here we go. Oh yeah, I will copy these lectures to the code. Okay, to the okay. Then you all can access the sample code. Okay. Okay. Now I go back to the using 2D. Okay. Yeah, there are many codes in this direction. Okay. Let's first go to the test mt.c. Okay. So yeah. Okay. So this is only just a CPU code. Okay. So you can compile with the G++. But then since this, I have used the machine twister. Okay. So you have to have the GSL library installed and also the GSL BLAS, okay, basic linear algebra subroutine installed. Okay, you want to your this code, okay, compiled in your system, okay, then okay, and otherwise you can use the rand, okay, yeah, and then still run, okay, the random number generator, okay, yeah, with the intrinsic subroutine by the library, that's okay, okay, okay. So if you use the machine twister, okay, then you have to include the GSL RNG, okay, this header file, okay, yeah. And then in the beginning, then you have to initialize the seed, okay. So so here I can enter any seed I like, okay, and then set the initial seed, okay, yeah, and then the RNG is the to yeah to the GSL RNG MT19937. Okay, so this random number generator. Okay, so allocate the RNG to this MT19937. Okay, so after initialization, then I can first do some simple tests. Some simple tests just to get a mean and the standard deviation. Okay, so for example, I have this dx. Okay, dx is the just get this uniform random number. Okay, by of using this machine twister. Okay, generate random number uniform deviation, and then I add all these numbers together. Okay, I get a mean, and the sigma is the dx square. Okay, and then after I normalize it by the number. Okay, how many number of this? How many total number of this? Okay, then I can mean. And then this sigma dx square, x square over the number minus mean square. Okay, then this the variance. Okay, and take the square root. Okay, is the standard deviation. Okay, so I get the mean and sigma. So this I get the mean and standard deviation here. Okay, so and then now I go to the Monte Carlo integration or one-dimensional integral. Okay. Yeah. Okay. So there's how many random numbers to be generated. Okay. So this enter how many. Okay. And this mean is for the simple sampling, and this is for important sampling. Okay. The mean one and sigma one. Okay. Mean and sigma is for the simple sampling. Mean and sigma one is for the important sampling. Okay. Okay. Now generate the random numbers. Okay, with uniform deviation. And then fx is a function f of y, okay. F, okay, is a function defined at the end, okay. There is a 1 over 1 plus x squared, okay. So I first get this in here, and then I go to f, okay, and this is fx, okay. So I get the one function, okay, and then one value, okay, one sampling, okay. Okay, the mean, okay, so I add all these samplings together and then divided by the total number, then I get the mean. And then this is so I get fx squared, I get a sigma. Okay, so I get this standard deviation, okay, and then divided by the number of sampling. Okay, so that is the error of the integral. Okay, sigma I. Okay. Okay. Similarly here, for the important sampling. Okay. So so this is the relation. Okay, between the x and the y. Okay, which you can obtain easily. Okay. So after integral. Okay. After integral, I mean the relation between x and y can be obtained. Yeah, analytically. Okay. Yeah. And the wave function is this. Okay. 4 minus 2x over 3. Okay. Okay, and then this is the capital F. Okay, it's fx over wx. Okay, so I've rewrite the w. Okay, the fx over w. So this is the since I don't need the fx anymore, so I just use the fx. Okay, yeah, because I already computed the sim here to accumulate, so I just use the same variable. Okay, for the important sampling. Okay, so you can see, okay, I just use the same expression, but this is the mean one, since the fx is computed by the fx divided by w. Okay, so that's it. So again, I compute the mean, is a mean one for the important sampling, and the sigma I, okay, for the important sampling. Okay, yeah. So this is the standard deviation divided by the number of measurements. Okay, and this is the error of the mean. Okay, yeah. So this is the output the results here. Okay, so let me go on. Okay, except okay. So yeah, I don't have to make again. Okay, so this is the previously I made here. Okay, yeah, let's see. Okay, now. Okay. So first I initialize the seed. Okay, initialize the seed of the random number generator. Okay, any number should fine. Okay, even 0. Okay, will work. Okay, so yeah, so the machine chooses the seed. Okay, you can enter any number, but not necessary for other random number generators. Okay, yeah, so the I. Okay, yeah, how many random numbers you want to generate? Okay, so this is the so this is the doing the one-dimensional integral. Okay, fx is 1 over 1 plus x squared. Okay, 1,000 points. Okay, now you can see. Okay, so this is a simple sampling. Okay, and this is the exact solution, and this is the important sampling. Okay, you can see the important sampling get the mean value closer to the exact solution, but the important point is here. Okay, this is the um, error. Okay, you see the important sampling, the error is much smaller. Okay, yeah, yeah, because the variance is smaller. Okay, yeah. Now, as I said, okay, the error is proportional to 1 over square root of the number of the measurement sampling. Okay, so I try again with a different number of the measurements. Okay, yeah. So instead of 1,000, I use the 4,000. Okay, then I would expect the errors decreased by a factor of 2. Okay, because 1 over square root 4 is a 1/2. Okay, so you can see, okay, the error. Okay, here initially is 6 times 10 to minus 4. Okay, here you can feel, right? You see the error is exactly is proportional to 1 over square root m. Okay, 1 over square root n. Okay, n is increased by a factor of 4, and the errors decreased by a factor of 2. Okay. Similar for the simple sampling is okay. 5 here, and then is 25. Okay, you see the error is proportional to 1 over square root of the n number of sampling. Okay, yeah, and the reason important sampling is smaller is because the sigma f. Okay, the sigma f now is the rescaled function. Okay, this is the sigma of the capital F rather than the small f. Okay, that is the sigma f over w. Okay, and that is a smoother. Okay, so you get a smaller error. Okay, so you can see the important sampling. Okay, is better. It's better. Okay, yeah, and no matter in terms of the mean value and also the error. Okay, so maybe quick. Okay. Okay. Now let's go back to the transparency, okay? And then we kept the essential ideas, okay? Again, okay? Yeah. Let me see. Yeah. Let me stop this, and then go back to the slide here. Okay. So yeah, you can see here. Okay, the relation between x and y is this. Okay, so exactly the yeah. Okay, and okay, yeah, yeah. So this is sigma f. Okay, yeah, and then this is 1 over n. Okay, so the error is proportional to 1 over square n times the sigma f. Okay, so now important samples make this sigma f, okay, smaller. Okay, so you have the sigma I is smaller. Okay, even though the sampling is the same, then the simple sampling, okay, sigma f is larger. Okay, yeah, because important sampling, the f, okay, is this guy here. Okay, f over w. But for the simple sampling, is the f itself. Okay, small f itself. Okay, so the transformer function f over w is smoother. Okay. Okay, so this is the basic idea of the importance sampling. Okay, and how do we sample the points with the distribution we want? Okay, the w. Okay, w is constructed. Okay, by ourselves. Okay, yeah, such that okay, f over w is very close. Okay, yeah, such that you can obtain the y x in terms of y. Okay, yeah, this integral can be done first, and the relationship between x and y can be obtained easily. Okay. But in general, it's difficult to find an appropriate way function Wx such that x can be solved analytically in terms of what? Okay. As I said, okay. That means these steps, okay, and these steps, okay, is not necessarily true in general, okay? So except for a few cases, in practical, generalize this scheme to very integrals in high dimensions. So you see, this is only one dimension, but you have a high dimension integral. Then how can you generalize this scheme? Okay, we have a very complicated integral, okay? So in that case, okay, then we have to go to some different algorithm, okay, even for any probability distribution, okay, and this will give you the important sampling, okay, this algorithm. That's called Metropolis algorithm, okay, yeah, and I think, yeah, I don't have the time today, and then I will continue, okay, next time, okay, yeah, but any questions up to this moment? Yeah, any questions? No? No? So, okay, the next time I will talk about the Metropolis algorithm, okay? Yeah, which can, very general algorithm, can generate the variables with any probability distribution, Wx, okay? Yeah, without solving this, doing the integral, and without doing the solving any equation, analytic equation, okay? Yeah. But of course, it has some its drawbacks, okay? Yeah. Okay. If there's no questions, anyway, you have any question, you can send me email, okay? Yeah. And yeah, I would, yeah, answer you as soon as possible. Yeah. If there's any, your questions cannot be resolved via email, then we can set an appointment, we can discuss, okay? Yeah. Okay. If there are no more questions, then let's conclude today's lecture. Okay. Yeah. See you all next time. Okay.
Thank you.
Okay, bye-bye.
Bye bye.
Thank you, teacher.
Bye-bye.